everyone. Today I'm going to talk about Linux Virtualization Based Security. My name is Angelina. I work at Microsoft. I've been there for a couple years now, and I've mostly just been working on this project. So I'd like to start off with our motivation for this. So every year there's an increasing number of kernel vulnerabilities that can be exploited. So our goal with LVBS is to harden the kernel by enforcing protections and also ensuring that critical system assets such as keys, passwords, and other secrets are untampered even if the kernel gets compromised. So LVBS is inspired by Windows Virtualization Based Security. It uses the hypervisor as well as hardware virtualization to protect the guest OS. We are targeting an open source architecture, so we are trying to upstream everything. We also want this to be both hardware agnostic and hypervisor agnostic. For this presentation, the examples are going to be with Hyper-V. So there are a couple of hardware requirements for LVBS. The first is second level address translation. This allows us to manage the VM memory, and it adds a secondary complementary layer of permissions that are controlled by the hypervisor. Intel implements this as their extended page table, or EPT, and AMD calls this their rapid virtualization indexing. We also need mode-based execution control. This pretty much just splits execute permissions into user execute and kernel execute. So this is what a Hyper-V system looks like without LVBS. We have a root partition and a guest partition. We have Hyper-V running in ring -1. We have the kernel space in ring 0 and user space in ring 3. So Hyper-V has this feature called Virtual Secure Mode. It introduces separate execution environments within a partition, and these are called VTLs. Hyper-V supports up to 16 VTLs, but in our case, we're only using 2. And the higher the VTL, the more privileged it is. These are some relevant VSM features. So there's virtual processor state isolation. This means that each VTL defines its own set of private VP registers. So if we do a context switch from one VTL to another, we need to store and restore the registers for that VTL. For example, going from VTL 0 to VTL 1 means we need to store the current state of VTL 0 registers and then restore the previously saved VTL 1 registers. VSM also has a memory access hierarchy with each VTL maintaining its own set of guest physical memory access protections. A higher VTL can impose memory restrictions to lower VTLs, and this is implemented through second level page tables. This means that for a guest to access memory, it needs to comply with both the guest page table permissions and the EPT permissions. So if, for example, the guest page table permissions are read-write, but the EPT only has read, then you can only read. Each VTL also has its own interrupt subsystem. This ensures that a higher VTL can process interrupts without interference from a lower VTL, since the higher VTL will have priority. This is a look at a high-level architecture. We have a guest partition with VTL 0 having a guest kernel, VTL 1 has our secure kernel. For our secure kernel, we actually use a minimal Linux kernel. We considered a few options with this, but that's what we're going with for now. On the guest kernel side, those boxes in purple are hypervisor agnostic. We have the memory protection framework, which I'll talk more about later, and an exception handler. We also have our VSM boot driver, which is used to bring up the secure kernel, and we have a VSM driver which takes requests from the hypervisor agnostic layer and sends them to VTL 1. In VTL 1, we have our bootloader to boot the secure kernel. We also have a VSM driver a memory protection interface and an interrupt and intercept handler. And there's also a VSM user interface, but that's mostly still a work in progress. Is this the same? I don't think I can.
Can you try with this one?
Yeah. Is this any better?
There's no button here. You can continue with this one, it's a bit better. And I'm gonna find some more.
Testing. Testing. I can try to speak a bit louder. Okay. This is our threat model. Our goal is to protect the kernel from user space attacker exploiting a vulnerability. We want this to be defense in depth, and by that we mean, well, the kernel itself has its own self-protections, but we want to add another layer of protections so that even if the kernel is compromised, you can't unset those protections. Our hypervisor is within the TCB since that's what we're using to enforce these protections. We also trust our guest kernel up until the very first unverified user space process. This is because we have secure boot enabled and we use that to verify the guest kernel. So we have a timeline of the boot sequence. The guest kernel starts to boot, it does its kernel initializations, and then towards the end of that, we start booting the secure kernel. So the secure kernel is booted by the guest kernel. So we have the secure kernel binaries in the VTL0 init-RD. We reserve a region of memory for the secure kernel. We verify the signatures of the binaries, and then we load the memory into, we load the secure kernel into the memory that we reserved and do our first call into VTL1 to boot the secure kernel. And after that, we apply our protections, and from there on, the init process starts, and we no longer trust our guest kernel. Okay, so this is how VTL0 and VTL1 communicate with each other. Currently, there are no processes running continuously in VTL1. VTL1 can be entered when a virtual processor switches from VTL0 to VTL1. This can happen a few ways. First is through a VTL call. This is a hypercall to request to transfer to a higher VTL. This chart shows some of the currently supported VTL calls that we have. Opposite to a VTL call is a VTL return, which is going from a higher VTL to a lower one. Another way that we can enter into VTL1 is through secure interrupts. These are, if an interrupt is received for a higher VTL, the VP will enter into that VTL. We've actually suspended timer interrupts while the VP is in VTL0. This is to avoid a bunch of unnecessary calls into VTL1. Secure intercepts will also bring us into VTL1. These happen when VTL0 violates a protection set in place by VTL1. Okay, so now we're going to start talking about some of the protections. The first is register pinning. So Hyper-V supports intercepting access to a number of registers shown on the right. We break this up into two sets. The first set applies to the table registers. For these, we block the write and raise the GP fault in VTL0. For the other registers, we allow a write if the new value is the same as it was pre-init. Otherwise, we block it and raise a GP fault. So this is showing how that works. VTL0 sets the security policy of the registers to protect. And since the registers are per VP, we have to do this for each virtual processor. So VTL0 calls into VTL1, and we save the register values, and that's our ground truth for when we try to write to a register that has an unallowed value. And then VTL1 will send a hypercall request to lock the registers. The hypervisor will apply the locks, and from this point on, any unallowed write request to the monitored register injects an intercept into VTL1. Okay, we also have memory protection. This uses the guest kernel memory protection framework. So towards the end of the kernel init, we walk the mappings to get the cumulative permissions using the guest page table permissions. We do a VTL call passing the kernel pages and their permissions to VTL1. VTL1 does a hypercall to Hyper-V to apply those permissions, and then we return back to VTL0. So this is what the memory permissions look like. RO data is read-only, text is read, and kernel execute. Our VTL1 memory space is set to no access, so that VTL0 can't tamper with it. And the rest of kernel memory is read, write, and user execute. And without LVBS, the permissions were read, write, and execute. So now if there's an EBT access violation, a memory intercept will be injected into VTL1 and a fault would be raised. So after applying those protections, we lock them down. This means that certain VTL calls are no longer valid, and any attempt to invoke them will return an error. So beyond this point, any changes to the EBT will require authentication. This is how we handle exceptions. These are raised for violating either register or memory access permissions. So say an attacker tries to write to read-only memory, then there will be a memory access violation raised. We will have an intercept in VTL1, which raises a GP fault in VTL0, and then kernel could panic if you have the config panic on oops set. Okay, we also have a set of KUnit tests written to test the register knocking and memory protections. These can be optionally built in and are run after boot using the debugfs file system. Here's a demo. There's no sound on it, so I'm going to talk over it. So this is running this is running the C* hack test. Okay, so this is running the C* hack test, which tries to write to that register. So first we read in the current value of the register, and then we try to write a new value to it, read in the new value, and then compare the old to the new value. If they're the same, then the test will pass, because that means that we blocked the write. And first we're testing this without LVBS enabled. So to run this test, we just write to this file. And we see that the test failed because the write successfully went through. Okay, and now we test it with LVBS enabled. On the left side is the VTL1 console output. And just show you the control registers are locked down at this point. So we're going to run the same test again, with this time with LVBS. And we see that our kernel crashed because we have panic on oops enabled. And on the VTL1 side, we got an intercept. And it tells you which processor, which register, and what the attempted write value was. So we've locked down the memory protections, but there are certain kernel features that we'll need to change permissions. So this is a table of the memory sections, the permission enforce with LVBS, the features that will cause an EPT violation because they require different permissions. So this part is mostly a work in progress, but this is our design principle for those text patching features. We call into VTL1 passing some information from VTL0 that is used to authenticate the text patching. We change the VTL0 memory permissions and copy that to VTL0 kernel memory and then undo it. I'll show an example with module loading, but first there is some kernel data that needs to be passed into VTL1 for the authentication. This includes build and boot time keys. These keys are passed into VTL1 and added to a key ring that's created. We also pass blackness keys and revocation certificates, and these are added to a blackness key ring in VTL1. And we pass kernel symbol table sections and read-only data sections. So modulating was one of those features I talked about. So when we load a module, VTL1 needs to independently authenticate the module. So VTL0 will pass the module, the original module blob. So VTL0 passes the original module blob along with the module memory established in VTL0 and some flags. VTL1 verifies that the module is signed by one of the keys that we had passed earlier, and then it reconstructs the module and compares that module memory to what was passed from VTL0. If that matches, then we call to the hypervisor to apply the permissions we need. And we return with a token that is used to identify the modules in this next part. So when we return, the module has been loaded, but the initialization of the module isn't complete. We need to reset the permissions of any init sections to read-write because those are going to be deallocated. And we also need to set any read-only after init sections to read-only. So we do this with a VTL call, which we call free module init, that causes a hypercall to apply those new permissions, and then we return back to VTL0. So this is a work in progress to support some other architecture-dependent features such as return trampolines, read links, and control flow integrity features like IPT. For these, we need some additional kernel data to be passed to VTL1. Okay, this is a pretty short demo on module loading. So I have this module. All it does is print hello world when it's loaded. So first we try to load the module without signing anything. And we'll see that it says the module failed to load here. And on the VTL1 side, it also says the module is unsigned, so verification failed, so it didn't load. Now we signed the module and try to insert it again. This time, the VTL1 console shows that the memory matched, so the module should be successfully loaded. We can check the message to see if it printed. And it did. So okay. Future work, we want to support the rest of the text patching features, such as jump labels, static codes, ftrace, kprobes, etc. And we also want to add support for kexec. And this is linked to our GitHub for the code. It's not up to date, but it should be updated soon. That's all. Thank you.
I have to read the mic to people if you ask question. Can you use the other one? So you just have to hold it to answer. Okay, who has question?
So for most of your BTL 0 clients, I saw that you're basically getting reduced and reduced memory sizes and registers that you can use. Can you have multiple BTL 0s, BTL 1s running at the same time?
No, we only have one VTL 0, one VTL 1.
Oh, so you can't like isolate. So basically if I have 4 levels, then the VTL 3 or something could would necessarily be higher permission than a VTL 1.
Oh yeah, you can add more VTLs like VTL 2, VTL 3, but for our implementation, we only have 0 and 1.
Gotcha.
So is the mode-based execution control what's allowing for the marking memory as kernel executable versus user executable, or is that a different Arch feature that I'm just not familiar with?
Sorry, can you repeat the?
So you mentioned earlier for the requirements for this that you had to have mode-based execution control enabled, and I think I just missed sort of what that entails. Is that what's providing that marking memory as kernel executable versus user executable, or is that a different thing?
Yes, mode-based execution control splits the execute bit into 2 bits, so there's user and there's kernel.
Cool, thank you.
Someone else? Right. Thanks a lot.
Thank you.